Okay. Right. We'll start. Am I audible? Am I audible? Okay, audible now? Right. Right. Good evening. Good evening, all. We'll start. So today we are in the 8th day of our S2A discussions. Right, day 8 of S2A, and my plan today is to do some viscosity questions. Right. In the last session, I think we had center of gravity. The one before we had surface tension, right? The one before we had surface tension. So likewise, we were covering some of the past papers from the S2A discussions. So far now, this day going on, and I think we covered linear motion, projectile motion, vectors, equilibrium of forces, right? So those are the things covered already. And now, since in the reverse class, since we have finished covering properties of matter, right? So I took I took surface tension as one S2A discussions in one of the last weeks, and today I'm taking viscosity, and soon I'll be taking elasticity as well. And since matter and radiation is ongoing now in the reverse class, upon the completion of matter and radiation, I'll be doing S2A sessions on matter and radiation as well. So likewise, somehow my plan is to cover all the past paper questions here of the ongoing and the already completed parts, already completed lessons, as you can get this advantage well before the exam, well in advance the exam, right? Otherwise, now if I do this like at the very last moment, just before the exam, sometimes you might not be able to join if you are if you haven't finished the things earlier. I mean, if you haven't finished the works, finish the studies that you need to do for the exam earlier, right? So that's why I started this well in beforehand, well in advanced. So then you can get the maximum out of this, right? You can get the maximum out of this. All right. Then without further ado, let's go into the discussion, right? Let me share my screen. Okay, my screen is visible, right? Visible now? Right. Let's start. First one. Right. First one. Which of the following pairs of physical quantities have the same dimensions? Work and power different because power is work over time. No, power is work over time or energy over time. Right. Power is work over time. Then work and work over time cannot be having same dimensions. Right. Stress and strain. Stress is a pressure because stress is F over A, right? F over A, and any stress has same dimensions as pressure, right? Any stress or any modulus has same dimensions as pressure. And strain is, what is a strain? Strain is E over L. Strain is E over L. Extension over initial length, right? Extension over initial length. Both are lengths. Strain is dimensionless, right? Then Young's modulus and pressure. That's the correct one. Young's modulus and pressure is the correct one. So you know any moduli is having same dimensions as pressure, right? Because let me write the equation of Young's modulus. F over A equals y times E over L. No? Equation of Young's modulus. E over L is dimensionless. E over L is dimensionless. See, E over L is dimensionless. This is dimensionless. There is a strain. E over L is a strain. Strain is dimensionless. So dimensions of y is equal to dimensions of F over A. Dimensions of F over A is dimensions of stress. Right? Stress is pressure. Stress means pressure. Then dimensions of Young's modulus is F over A. F over A. Right? Which means this equivalent to dimensions of pressure. No need to find. Right? F over A, pressure equals F over A. That's a general equation of pressure. Pressure equals F over A. Right? Then that's the answer. And fourth one, coefficient of viscosity and surface tension. No. Coefficient of viscosity, eta. Eta is ml minus 1, T minus 1. And surface tension, dimensions of eta. And dimensions of surface tension is mt minus 2. Dimensions of surface tension is mt minus 2. Force and momentum, no. Force and momentum in because force is, right, they are popular dimensions, you know. Force is mlt minus 2, right? And momentum is mv, right? That is mlt minus 1, right? They are very popular dimensions, we know, right? It's an easy one. Second one. In the apparatus shown, water flows at the same rate through two narrow tubes of lengths L and 2L and radii A and A over 2 respectively. If the tubes are at depths H1 and H2 below the surface of water, then the ratio, then the ratio H1 over H2 will be. Then the ratio H1 over H2 will be. Right? Ratio H1 over H2 will be. Okay. Then if you have horizontal tubes, we know we have Poiseuille's equation of viscosity. We have Poiseuille's equation. Right? If I quickly recall the equation, Poiseuille's equation is V over T equals phi delta P R to the power 4 over 8 theta L. Poiseuille's equation of viscosity. Right? And now we can apply this and we need H1 over H2. Right? We can apply this and it says same rate. V over T. Volume flow rates are same. Now it says, right? And when we write pressure differences, we can write pressure differences as H rho G because of this. Right? Look at this idea. This is open to atmosphere, P naught. And this end is open to atmosphere, P naught. Right? Now, if I write pressure at this point, right? Pressure at this point, let's say A and B. This color is visible, right? A and B. Say pressure at A and B, pressure difference. Then pressure at A can be written as P naught plus H rho G. Right? And pressure at B is P naught. Then when I need PA minus PB, pressure difference, PA minus PB, P naught cancels and only H rho G comes. Right? Going to use this idea here. When we write the pressure difference, only H rho G comes. Right? Now let's apply this for these two scenarios given. It says V over T are equal, no? Right? Then let's start off from there. Right? Let's start off from there. Then it says V over T are equal. Then V over T equals V over T. If I expand 1 V over T using the first tube, right? Phi delta V, pressure difference of the first tube is H1 rho G. Right? Like this, according to this one, H1 rho G. Then R is given as A to the power 4 over 8 eta. Length of the first tube is L, right? L, something like this, equals from the other tube, phi H2 rho G, A over 2 whole thing to the power 4 over 8 theta. Length is 2L, right? Some terms are cancelling. Phi cancels, rho G cancels, phi to rho G to, right? 8 theta to L to L, those things get cancelled, right? And if I simplify a little bit further, in this side, H1, A to the power 4 remains. On the other side, H2, A to the power 4 and 2 to the power 4 comes. 2 to the power 4 is 16, no? 2 times 2 times 2 times 2. 16. Then 2 was here and 2 into 16. Now this A4 also cancels. What's the ratio asked? H1 to H2, right? Then ratio H1 to H2 is, right? Here only 32 remains. Then 1 over 32. 1 over 32, right? A Poisson calculation. A Poisson calculation. A Poisson calculation. Poisson's equation. Right? A Poisson calculation. Next. Third one. An air bubble is liberated from the bed of deep sea moving upwards. Which of the following graphs best represents the variation of speed of air bubble with time? Speed of air bubble with time. So this is one of the graphs we draw in the class, right? This is one of the graphs we draw in the class when we are discussing theories, isn't it? An air bubble is liberated from the seabed of deep sea moving upwards, right? Moving upwards. Which of the following graphs best represents the variation of speed v with time? Okay, v with time. Then let's do this way. Now, if we argue a bit, listen, if we argue on this a bit, so we know this speed can be written as this, no? If we are to use the equation of, no, let's go to the basics. Air bubble. An air bubble is liberated from the seabed. So it is moving upwards. It is moving upwards means upthrust acts and mg acts and viscous force effects. Viscous force acts. Right? Now, if we check this acceleration, apply F equals ma upwards. Apply F equals ma upwards. Right? Then u minus mg minus F equals ma. Right? Then if you expand this F, we know 6phi eta RV equals ma. 6phi eta RV equals ma. Right? Then when it as it moves forward, as it moves not forward, upwards and moving upwards, which following which of the graphs, right? As it's moving upwards, what we know is, what about pressure? Pressure decreases, no? Right? Because pressure of a liquid depends with the depth. Pressure is h rho g, delta p. Delta p of a liquid is h rho g. So when h decreases, when depth decreases, pressure decreases. Right? When pressure decreases, pressure inside the air bubble decreases. When the pressure inside the air bubble decreases, its radius decreases. Its radius decreases, no? When radius decreases, this term decreases. Right? When pressure decreases, its radius decreases. So this term decreases. When this term decreases, a deducting term decreases. When a deducting term decreases, its acceleration increases. Its acceleration increases. That's it. Only increasing acceleration curve we have here is 2. Only increasing acceleration we have here is 2. Then it has to be 2. Then it has to be 2. Right? Considering the pressure difference occurs here. Right? Consider the pressure difference. When the air bubble goes upwards, pressure decreases. When pressure decreases, its radius decreases. Right? Let's move on. 4. Which of the following statements regarding the rate of flow of viscous liquid flowing steadily through a narrow tube is not correct? Right. Again, that is from Poisson's equation, no? Right? Poisson's equation. V over T. This is the equation. Phi delta P R to the power 4 over 8 theta L. Right? Now check what is given. Check what is given. Which of the following statements is not correct? Okay. the rate of flow is directly proportional to pressure difference between ends of the tube. Delta P is pressure difference. So it is directly proportional, that is correct. Directly proportional, that is correct. The rate of flow is directly proportional to the fourth power of the diameter of tube. If that is proportional to the fourth power of radius, right? We know diameter means 2 times radius. So radius is also d over 2. If you apply d over 2 instead of r, again you are getting, instead of this, what you are getting is d to the power 4 over 16. Right? So still you have a fourth power. That's correct. That's a correct statement. Right? The rate of flow is inversely proportional to the coefficient of viscosity. It's correct, no? See, coefficient of viscosity is here inverse. Correct. The rate of flow is inversely proportional to the length of tube. Because L is here, inversely proportional to the length. Last one, the rate of flow is independent of the pressure gradient. What is pressure gradient? Pressure gradient means delta P over L. This is called pressure gradient. V over T is proportional to gradient of pressure. You can see it from the equation. It is proportional to gradient of pressure. Then we can't say it's independent. That's wrong. So the answer is 5. Right? That is something in the equation. Then how come it be independent? It's something in the equation. Right? Next. It's an easy one. 5. Okay, this is a good one. See, a sphere of radius A attains a terminal velocity V0 when it falls down in a fluid of coefficient of viscosity eta1 and density d1. Okay, the same sphere is found to attain the same terminal velocity V0 when it rises up in a different fluid of coefficient of viscosity eta2 and density d2. The difference of densities of two fluids d2 minus d1 is proportional to. Okay, so for terminal velocity, we have a proved equation. What's the proved equation of terminal velocity? See, what's the proved equation of terminal velocity? Proved equation of terminal velocity is V equals 2r squared g rho object minus rho liquid over 9 meter. No? This is a proved equation for terminal velocity. Right? Then, what if we apply this for these two scenarios? Because we have proved this equation when a sphere goes downwards and upwards both. Right? When it travels downwards, rho O is greater. When it goes upwards, rho liquid is greater. Then with that, these two terms are switching. Right? With that, these two terms, only these two terms. With that, these two terms are switching. Right. Now let's apply this for these two scenarios given. A sphere of radius A attains a terminal velocity V0. Then V0 equals 2 radius is A, 2a squared g. Right? When it travels downwards, let's assume density of this sphere as d. Then if it is moving downwards, it should be d minus d1. Right? d minus d1 over 9 eta 1. When it goes upwards, this is when moving downwards. When it is moving upwards, same V0 is attained. It says then 2a squared g. Right? If it goes upwards, this should be d2 minus d. Because if the density of liquid is greater than the density of object, only it travels upwards. Right? 9 eta 2. Right? Since we need this difference, d2 minus d1, no? d2 minus d1. Shall we subject d minus d1 from these equations? That would be easy, no? Let's subject this. Then, if I subject d minus d1 from this equation, what comes is 9 eta 1 times V0 over 2a squared g. Right? And if I do the same here, if I subject d2 minus d, right, 9 eta 2 V0 over 2a squared g. Right? Now let's assume or label these two as equation 1 and equation 2. Now I need to get the difference. At these two. Right? To get the difference at these two, 1 plus 2. Then d2 minus d1 comes because d cancels. plus d to minus d cancels. And from here, these terms are common, no? 9 is common, right? Then V naught is common. What else? 2a squared g, 2a squared g is also common. Then when we add these equations, eta 1 plus eta 2 remains, right? Now it's asked, then it's proportional to. Then you can remove the constants. Proportionality is asked, no? You can remove the constants. You can remove the constants. Let's isolate constants here. 9 is a constant, right? And 2g is a constant. And these are the variables. Eta 1 plus eta 2 V naught over a squared. These are the variables. Then it is proportional to this part. If you keep the constant aside, it is proportional to this part. Eta 1 plus eta 2 V naught over a squared. Eta 1 plus eta 2 V naught over a squared. First one, right? First one. It's a good question. It's a good one, right? Stay down. It's a good one. Next. A tank carries a horizontal narrow tube at the bottom as shown in the figure. In order to maintain water level at height h, water should be supplied to the tank at a constant rate of Q. The rate at which the water should be supplied to the tank to maintain its H water level at 2H is. Okay. Again, you can write the pressure difference as I did before, right? This is open to atmosphere P naught. This is also open to atmosphere P naught, right? Now, if I need to write pressure difference here, right? Say A and B, right? Then if I need to write pressure difference, PA can be written as P naught plus H rho G, and PB is P naught open to atmosphere. Now the pressure difference here is PA minus PB. That is exactly H rho G. That is exactly H rho G. So pressure difference is written as H rho G. Now to connect this with the rate of volume flow, apply Poiseuille's equation. V O T equals phi delta P R to the power 4 over 8 theta L. Right. Now let's remove constants. That is easy. Let's remove constants. Phi is a constant. Delta P is different. So don't remove delta P. Delta P is different. And radius is constant, same tube. 8 is constant. Eta is constant, same liquid, same tube, L is constant. Right? Then at once, I can have something like this. It says V over T here is proportional to delta P. Then I know delta P as this is my delta P. Right? I know delta P as H rho G. Now from this, rho and G are also common. Right? Very straightforward. See what has happened now? Which means V over T is proportional to H, no? V over T is proportional to H. Now initially it's given as Q. Let's apply this for these two scenarios given now. That's it. Let's apply this for these two scenarios given. First scenario is Q is proportional to H. Second scenario, say Q dash proportional to 2H. Divide these two, right? Q dash equals 2Q. Because if pressure difference, if the height is doubled, which means Q should be doubled according to this equation. Very simple. Then 2Q. Another Poiseuille question. A Poiseuille's equation question. Another Poiseuille question. Another Poiseuille one. Right? 7. Two small metal spheres of equal radii, but different densities, ρ1 and ρ2, are released from rest inside a tall vessel filled with a liquid of density ρ. Right. If the terminal velocities reached by the spheres are v1 and v2 respectively, the ratio v1 to v2 is equal to. Okay. Then this is a proved equation for terminal velocity. No? We have a proved equation for terminal velocity. That is, terminal velocity equals 2r squared g rho object minus rho liquid over 9 eta. Right? Then we can apply this for these two scenarios given. Right? For these two scenarios given. First one, terminal velocity is V1 equals, their radii are equal to 2r squared g, right? Densities are different, right? Liquid density of liquid is rho released from rest. Okay, then this should be rho 1 minus rho, no? Rho 1 minus rho over 9 eta. And for this one, V2 equals 2r squared g rho 2 minus rho over 9 eta, right? Then the ratio V1 to V2, divide these two. Very straightforward. Very straightforward. Divide these two. Divide these two. When it is divided, 2r squared g to 2r squared g cancels, 9 eta to 9 eta cancels. Then V1 over V2 comes as, from here rho 1 minus rho, and from here rho 2 minus rho. Right? Rho 1 minus rho over rho 2 minus rho. It's 4. A small calculation. That's a small one. A small calculation. Right? That's not a big deal. A small one. Right? They are from Stokes equation, and terminal velocity of a sphere is a proved equation. Right? Terminal velocity of a sphere is a proved equation. You can apply it anywhere, whenever you need. That's a proved equation. That's a proved equation. Next. 8. The liquid flow through capillary tubes which are not connected to each other under the same pressure. Under the same pressure difference. The internal diameter of two tubes are in the ratio 2 to 1. Okay. And the lengths are in the ratio 1 to 2. Now, like this, two tubes are there, right? Two tubes are there. Two tubes are there, right? And pressure differences are same. Delta P are same. Delta P and delta P, they are same. Internal diameter of two tubes in the ratio 2 to 1. Always ratios between diameters and radii are same. Right? Ratios between diameters and radii are same. Because diameter over 2 is radius. So as a ratio is same. Ratio is same. Then if I go with the radius 2 to 1, no. Then if radius of this one is 2r, radius of this one is r. And lengths are in the ratio 1 to 2. If length of this one is L, length of this one is 2L. Something like this. The ratio of the rate of flow of liquid through. Okay. Then apply Poiseuille's equation. A direct application of Poiseuille's equation. V over T equals 5 delta P r to the power 4 over 8 theta L. We can cut off the constants because you are going to find a ratio. Cut off the constants. Phi is a constant. Delta P is same constant. Then 8 is constant. Eta is constant. Right? The rest remains. Which means, right? Which means V over T proportional to R to the power 4 over L. No? Apply this for these two scenarios given. Apply this for these two scenarios given. The ratio of the flow. So let's assume this as Q for our is. Then for the first one, Q1 proportional to R to the power 4 and 2R to the power 4. 2R to the power 4 over L is L. 2r to the power 4 is 16r to the power 4. No? 16r to the power 4 over L. For the second one, say Q2, it's proportional to r to the power 4 over length 2L. Right? Divide these two. Divide these two. Then Q1 to Q2 equals, right? When you divide, r to the power 4 to r to the power 4 cancels, L to L cancels. Then from the first one, 16 remains. Right? And from the second one, 1 over 2 remains. 1 over 2 remains. Simplify this. So it is 32. This 32. Right? 32. Then Q1 to Q2 should be, this is 32 means 32 to 1, no? 32 to 1. Right? Another calculation from Poiseuille's equation. 32 to 1. Right? Another one from Poiseuille's. See how these equations are used. We had only 3 equations in viscosity. We had only 3 equations about viscosity. This is how these equations are used. Right? And another reminder, we'll be having the graphing seminar for 27 batch graphing seminar on Sunday 15th at 7 p.m. Right? Doesn't matter whether you are in 26 batch or 27 or whatever it is, right? If you are not comfortable plotting graphs, right? If you are not comfortable arranging the terms, rearranging the given terms as to plot a graph, and once terms are rearranged to plot the graph in the correct shape, trigonometric graphs, right? And linear graphs, non-linear graphs, inverse graphs, right? If you are not familiar, you can join there on 15th Sunday, right? Physically, I'll be at Lisa Center Horna, and online will be on YouTube Live. You can join the session somehow and get it covered there, right? Because around 15% of marks is allocated, 15% from final 100 for marks for graphs, right? That's the thing. 15% means that's a huge amount. 15% is a very huge amount. That's a huge amount. Okay, 9 and 28 batch classes are also started. If you have your maybe younger sisters, younger brothers, friends, so relatives, someone like that, you can also share the message that 28 batch is started, and the class is conducted now for 2 days. They can get the recordings if they are joining this week, right? Recordings of previous 2 weeks, and class is on Tuesdays at 3 p.m. Right? If there's anyone, you can convey the message. 9. Consider the following statements regarding the flow of a viscous liquid through a narrow tube. Right. Then through a narrow tube. For tubes, we have only Poiseuille's equation. Then this is something from Poiseuille's again. V over T equals phi delta P R to the power 4 over 8 theta L. Right. 8 theta L. 8 theta L. Right. First one. Speed of flow is maximum along the axis of tube. Yeah. That is not in the equation, but we know about the speed of the flow here, right? If I draw this as arrows, speed of the center, right, or the axis is highest because adhesive force with the tube and the molecules are minimum at the axis, right? There are adhesive forces, no, we have learned in surface tension, right? So more closer to the tube, wall of the tube, adhesive force increases. Since that adhesive force increases, right, flow of the liquid, right, rate of flow of the liquid decreases a bit like this. It decreases a bit like this, something like this. So this has the maximum speed. A is correct. That has a maximum speed. A is correct. Rate of flow of the liquid is proportional to the internal cross-sectional area of tube. There's no cross-sectional area term here in this equation. See, there's no cross-sectional area term in the equation. So B is wrong. B is wrong. Right? B is wrong. And C, rate of flow does not depend on the temperature of liquid. Wrong, because eta changes with temperature like this. Right? So we got this in the class. Eta changes with temperature. Say theta. Right? Eta changes with temperature like this. When eta changes, VOT changes. So this is also wrong. This is also wrong. Right? According to the equation, when eta changes, VOT changes. That's also wrong. So only A is true. Right? A small argument from Poiseuille's equation, again, mainly from Poiseuille's equation. Other than that, there are a few more things you should know like this. Right? Right. Next. The viscous force acting on a sphere moving in a fluid dish. Okay, viscous force acting on a sphere. For spheres, we have a dedicated equation. For spheres, we have a dedicated equation, that is Stokes equation. Stokes equation, F equals 6 phi eta RV. Stokes equation. Stokes equation. Right? Directly proportional to viscous force again, right? Viscous force is F. Directly proportional to the velocity of sphere. Yeah, that's correct, no? F and V are proportional. This is velocity of sphere. F and V are proportional. A is correct. Directly proportional to mass of sphere. No. No mass term here. No mass term here. Wrong. Inversely proportional to the radius of sphere. No, for radius also that is direct, no? See, F and R radius, that's also direct. So this is wrong. Then again only A. Only A. That's an easy one from Stokes equation. From Stokes equation. That was an easy one from the Stokes equation. Right, take it down and clarify if any doubts. You are just 21 weeks ahead of the exam now. Right, 26 batch. 21 weeks ahead of the exam. Exactly 21 weeks and 2 days. 21 weeks and 2 days. Right, 21 weeks and 2 days. A very small period of time. A very short period of time. A very short period of time. Right. So when we are busy with our things, right, always time flies. Then time flies, time will fly, right? So we have to utilize that time as to get the maximum benefit out of this. That's the thing, right? You have to balance 3 subjects, right? Not only physics, not only chemistry, not only combined maths or bio, right? You have to balance 3 subjects. So balancing all 3 subjects is not easy unless you properly manage your time. That's the thing. Okay. 11. 2 masses, A of mass m and B of mass 2m, but of the same volume, are released from rest at time t equals 0 at the surface of a deep pond. Which of the following graphs best represents the variation of the speed of 2 masses from t equals 0 to t, until they reach the bottom of the pond? Okay. Now, since I need to incorporate this with mass, right? Since I need to incorporate this with mass, let's go to the fundamentals we know. Right. Now, if these two are the spheres, right? Same volume, same volume. If these two are the spheres, right? We know their masses are different now. Mass of one is mg, mass of the other one is 2 mg, and mass of this one, sorry, upthrust acting on here is u. Upthrust here is also u because their volumes are equal, right? Volumes are equal. Volumes are equal means their radii are equal, no? Right? 2 masses. Their radii should be equal. Then F is also equal because F is given by 6 phi eta RV. If volumes are equal, radii are equal. If radii are equal, F are also equal. Right, now, if I check their initial acceleration, see what happens. अपनी initial acceleration check करो. If I check their initial accelerations, initial accelerations apply F equals ma downwards. We have proved this in the class also as maximum acceleration of an object, right? So as downward forces, let me apply for the first scenario. Mg minus u minus F equals ma. Mg minus u minus F equals ma. Right, now from these two, u and F are constants for both scenarios, no? U and F are constants. Right, mass changes from m to 2m. There is an increase of mass in the second scenario. Then when mass increases, what happens is left hand side of this equation increases. When left hand side increases, right hand side should also increase accordingly. Then probably A increases, which means acceleration of B should be greater than acceleration of A, no? Isn't it? Acceleration of B should be greater than, because mass of B is B of mass 2m. Mass of B is 2m. So higher the mass, higher the acceleration. Higher the mass, higher the acceleration. A small decision we can make. If acceleration is higher, graph should be graph of A. This is a VT, right? Graph of A should be above graph of B should be above A. Higher acceleration means higher gradient. Higher acceleration means higher gradient, right? Higher acceleration means higher gradient. Then we have this option here. We have this option here, 3. But the thing is this. Listen, there's one more thing. Listen, there's one more thing. The other thing is, if you check the time it takes to reach terminal velocity, higher acceleration means terminal velocity is reach time taken to reach terminal velocity is short, higher acceleration, no? Higher acceleration. When the acceleration is higher, it reaches the terminal velocity quickly when the acceleration is higher. So that's how I omitted 2 and stick to the third one, because higher acceleration means time takes for the terminal velocity should be less, right? But the thing was, this was given all in the exam, because now when we argue using mass here, the mass term is already here, no? On the right hand side. Then with that mass term, it is a little bit difficult to build up that argument. It is a little bit difficult to build up that argument. So therefore, this question was considered as an all question in this exam, right? This question was considered as an all question in this exam, right? Now, otherwise, if we argue using masses, 3 comes. If we argue using masses, 3 comes. But when both right hand side and left hand side changes, the argument is kind of erroneous. That's the thing, right? That's not a solid argument when both sides are changing, right? So therefore, this was given all in the exam, right? 12. Graphing. A small raindrop releases from cloud at a height h above Earth's surface. The variation of the speed v of raindrop with height h from Earth's surface is best represented by. Okay. Say this is the Earth's surface. Say this is the Earth's surface, right? And this drop is released somewhere here, right? Capital H, right? Capital H above the Earth's surface. Now let's say after some time, this has fallen up to here, right? Say it has fallen a distance x. It has fallen a distance x, right? Now the height from ground is h minus x. No? Height from ground is h minus x, right? To write the velocity here, right? We know you can apply a linear motion equation, or we have proved it in the class, right? If an object comes from rest, if an object released from rest falls h distance, its velocity becomes root 2gh. Then if it has fallen x distance, its velocity should be root 2gh, right? Root 2gh. If you don't know, this is how this is. Now this is root 2gh. This velocity should be root 2gh. If you don't know this is how it can be derived. You can apply an equation like v squared equals u squared plus 2as downwards. Then v squared equals u squared is 0, 2gx. Then it gives v equals root 2gx. Right? So that's how it can be done. Then the variation of the speed v of the raindrop with the height from Earth's surface. From the height from Earth's surface. Now, height from Earth's surface in my case is h minus x. Right? Height from Earth's surface is h minus x. Then we can write this as, right? Let's rearrange. Now, in the graphing session that we are going to have on Sunday also, this is what we will be discussing about graphs, right? Same thing. Then this is v equals root 2gx. No? To include this height from ground instead of x, what if we write, I need to include this from ground. And x then what can we write? What if we write this way? The variation of the speed of the raindrop with the height h from Earth's surface is. Height is measured from Earth's surface. Then let's label this the other way. See, let's label this the other way. Height is measured from the Earth's surface. Then, right, let's keep this as x, but height is measured from the Earth's surface. Let's keep this as x, and this is measured from the Earth's surface. Say simple h. That is given as simple h in the graph. Right. Root 2gx. Now we know x can be written as, right, if needed, x can be written as h minus h, no? Using the graph, using the diagram, x is capital H minus simple h. Then this is root 2g. See how I rearrange this? Root 2g x ki lagi x is h minus h. Now this shape is root 2gh minus 2gh, right? This is not an exact standard curve, but the standard curve we know is this. The main idea is the standard curve we know is this. We know y equals m root x. We know how to plot y equals m root x. Y equals m root x is something like this. Something like this. Y equals m root x is something like this. M root x. Now, to get an idea about this equation, right, what you can do is check its endpoints. Check its endpoints. That's better. Now, when the motion starts, capital H equals simple H, no? Distance from ground is equal to capital H, no? Then see, when motion starts, what about V? Check it out. When H becomes 0, when capital H becomes 0, when simple H becomes 0, if you need to check this out like this, when simple H equals 0, go to the equation here, it says V equals root 2gh. Then we should start from a non-zero value. And then you can check when V equals 0. When V equals 0, what happens is H equals H KL. If you simplify this, H equals H. Then starting from V, right? And when V equals 0, simple H should be equal to capital H. Simple H should be equal to capital H. And this is a non-linear variation. This is non-linear because this is inside the root, non-linear. Then only option we got is this one. Only option to satisfy everything is this one, right? So this is not an exact standard curve, but yet this is how we argue and draw this. Right? Get the idea. Understand the concept. Understand the concept. Next. Now here, if M1 and M2 are not visible, it seems that is not visible. No? This one is M2 and this one is M1. Right. Two spheres of each of radius A, but of different masses, M1 and M2, M1 greater than M2, move down at their terminal velocities in a liquid of viscosity eta. At the instant shown in the figure, the separation x between the two spheres is being separation. Okay. To find the separation per second value, then let's find their terminal velocities. Right. Now we need to write terminal velocities using masses. Right, using masses. Then don't use the proved equation because in the proved equation we don't have mass. Then go to the basics and apply this. Now, when a sphere moves downwards, mgx, F viscous force acts, upthrust acts. Right. So we know at terminal velocity, forces are in equilibrium because terminal velocity is a uniform velocity. F plus u equals mg. Right. And F can be expanded as 6 phi eta RV plus U equals mg. Right, let's apply this equation for these two now, separately. Right, different masses move down at their terminal velocities in a liquid. Okay, then let's apply this separately and find their terminal velocities as V1 and V2. Like this. Then for first one, 6 phi eta A V1 plus U, each radius A, no, which means volumes are equal. Radius is equal, which means volumes are equal. Volumes are equal means, right? Upthrusts are equal, right? When radius are equal, volumes are equal. When volumes are equal, upthrusts are equal. Right? Then same upthrust. U equals first one M1G. For the second one, 6 phi eta A V2 plus same upthrust, but M2G. Right? Now, you can clearly see from these equations, right? Higher the mass, this side increases. Since upthrust is a constant, higher the mass, higher the velocity, no? Higher the mass, higher the terminal velocity. Then higher velocity is with V1. Then to find the difference, let's get the difference. To get the difference, subtract these two equations. Then let's label this as 1 and 2. 1 minus 2. Subtract these two to get the difference. 1 minus 2, right? Then 6 phi eta a is common. V1 minus V2 comes. U cancels, right? From right hand side, M1 minus M2 G. G is common, right? Then see the difference V1 minus V2. V1 minus V2 is M1 minus M2 G over 6 phi eta A. M1 minus M2 is 6 phi eta A. Now you have to decide whether it's decreasing or increasing. Difference of velocities are there. Difference of velocity is the rate of increase in the gap per second. No? Velocity is meters per second, right? So that is the rate of increase in the gap per second, per unit time per second, right? එහෙනම් මේක දන්නවා කියන්නේ වැඩේ හරි. දාන්න මේක තියෙන answers මොනවද කියලා. මේක තියෙන answers මොනවද කියලා බලන්න. M1 minus M2G, M1 minus M2G over 6 phi eta A, right? 3 එකේ තියෙනවා, it is in 3 and 5. Increase or decrease කියලා කියනවා. Now go back to the diagram. M1 is higher. M1 is above. M1 is above and its velocity is higher. V1 is higher. And M2 is below. Its velocity is lower. V1 is higher. Which means V1 is reaching V2. Sorry, M1 is reaching M2. M1 is reaching M2 with the higher velocity from behind. So they are getting close to each other. So they are getting close to each other. Since they are getting close to each other, they decrease. The gap decreases, right? So that is something from the diagram, because higher velocity is coming from the top, so the gap decreases. Gap decreases, right? That's also kind of a good one, right? Kind of a good one, right? Take it down. Next, 14. A small ball starting from rest rises through a viscous liquid and reaches its terminal velocity. Consider the following statements. Okay, a small ball. The upthrust on ball is greater than the weight of ball. Yeah. If this is moving upwards, right, that is because of this. That is because of this, right? If that is moving upwards, viscous force is F, right? If that is moving upwards, right? Moving upwards, no? Moving upwards. Now, if these densities are, say, density of the surrounding medium is rho liquid and density of this one is rho O, if that is moving upwards, that is because rho L is greater than rho O. When rho L is greater than rho O, upthrust is greater than mg. Upthrust is greater than mg. Right? Our step back on a right? Now, if I need to compare these two, upthrust and mg, we know upthrust is V rho G, no? V rho liquid G. M is V rho object G. When rho liquid is greater than rho object, this is greater. So upthrust is greater. Sorry. Sorry. Then it says the upthrust on the ball is greater than the weight of the ball. Correct. Upthrust on the ball is greater than weight of the ball. Correct. Second one. At the initial moment of the motion of the viscous force, initial movement of the motion, the viscous force of the ball is 0. Correct. Why? It is given by F equals 6 phi eta RV, Stokes equation, right? Initially, velocity is 0, right? Since initial velocity is 0. When initial velocity is 0, F becomes 0. F is 0, B is also correct. F is 0, right? F is 0, so B is also correct. B is also, what happened? Right. B is also correct. B is also correct. C. The acceleration of ball remains constant until the ball reaches the terminal velocity. No, never. Any object which is reaching a terminal velocity goes with a decreasing acceleration. Any object which is reaching a terminal velocity travels with a decreasing acceleration. Right? That is a decreasing acceleration. Right? So if you don't know it, this is how it is proved. If you apply F equals ma upwards, right? To check the acceleration, if you apply F equals ma upwards, to check the acceleration, it is u minus mg minus f. F is 6.5 eta, r we know, equals ma. See what happens? Now, when it is released from rest, its velocity increases. When its velocity increases, this whole term increases. When this term increases, left-hand side of the equation, that is the subtracted term, decreases. So A decreases. Right? Any object which is reaching a terminal velocity is traveling with a decreasing acceleration. Keep that in mind. That's a decreasing acceleration. So this is hell no, that is totally wrong. The acceleration of the ball remains constant. Totally wrong. Then A and B. A and B. Right? Next. Two small plastic spheres, A and B, of which A is hollow and B is solid. Okay, is made of same material. A is hollow, B is solid. Something like this. A is hollow and B is solid. A and B. A and B. Something like this. Made of same material, same density. Same density. Which means now if I need to argue on these masses, MA and MB, let's say, right? Same density, no? Same density. Then less volume is here. Less volume is here. Since that's a less volume, higher mass is MB. Higher mass is MB. Because clearly I can see VA is less than VB. That's a less volume of substance. That's a less volume of substance. VA is greater than, VA is less than VB. So does mass is also less. Right? Made of same material, having the same external radii. Okay. Same external radii. And released from rest from a tall building. Sorry, released from rest from a tall building. Both spheres reach their terminal velocities before hitting the ground. When the spheres reach ground, okay. First one, the speed of A is greater than the speed of B. Speed of A is greater than the speed of B. To check the speed, apply this from fundamentals as before. See, in which one? This one with the mass, right? If you need to incorporate mass, this is how you should apply. If you need to incorporate mass, then we can do the same here, right? We can do the same here. Now they are coming downwards. When they come downwards, mgx, upthrust, f. Then at terminal velocity, right? At terminal velocity, terminal lagi check karo. At vt, terminal velocity, acceleration is 0, which means u plus f equals mg. Then u plus f is 6.5 eta rv equals mg, right? U is a constant because their external radii are same, which means volumes are same. U is a constant. Then higher the mass, higher V, no? Right? V and M are proportional according to this. V and M are proportional. Higher the mass, higher the V, which means VB should be greater than VA. The speed of A is greater, wrong. Speed of B is greater. Speed of B is greater. The viscous force on A is less than that on B. Viscous force. See, viscous force is 6.5 eta rv, no? Right? Then higher velocity. Higher velocity is with B. Higher velocity is with B. Higher the velocity, higher the viscous force, no? Higher the velocity, higher the viscous force. Which means lesser the velocity, lesser the viscous force. Right? Lesser the velocity, lesser the viscous force. Then the viscous force on A is less. That is correct. 2 is correct. Viscous force on A is less. Correct. Third one. The viscous force on B is less than. No. A has taken a shorter time than B. Higher velocity takes a shorter time. Higher velocity is B. So B takes a shorter time. 4 is also wrong. Both spheres gain the same speed. No, that's also wrong. So answer is 2. See? Small arguments. Small arguments. Right? Small arguments. See how it goes. Right? Pretty simple arguments. As long as you know these fundamentals. Now you can't apply fluid equations because a hollow sphere is given. right? We are proving the equation of terminal velocity for a solid sphere. We are proving the equation only for a solid sphere, not for hollow spheres. Right. 16. A tiny sphere with static charge plus q starts to fall through air under gravity at a equals 0. After the sphere has reached the terminal velocity, a vertical upward electric field E of constant magnitude is applied. A short time after the sphere changes direction of its motion, the electric field is removed. All right. Then initially it's reaching a terminal velocity, right? So say this is moving downwards. Then at some point it is reaching plus q charge, right? Plus q charge. There's a small link with electric fields here. Charge is given, right? So at some point it has reached a terminal velocity like this. Say Vt like this. And then an electric field is applied. An electric field is applied upwards, right? Then it creates another force and acceleration due to electric field upwards on this. Then what happens is it's decelerating and going to switch the direction of motion. Switch the direction of motion. If the direction of motion is switched, right? If the direction of motion is switched, motion should be at two sides. We are going to plot a velocity time graph. Then it should be in both plus and minus sides. 1 is wrong and 4 is also wrong because I can't see any negative sides in 1 and 4, right? Okay, then suddenly electric field is removed again and the electric field is removed again. If the electric field is removed, if E is 0, acceleration due to electric field becomes 0. Then again, the object is reaching the terminal velocity under gravity. Again, the object is reaching the terminal velocity under gravity. And terminal velocity depends only on these things. See, 2r squared g, rho object minus rho liquid over 9 eta. Right? Now, even if the electric field is removed, 2 is same, r is same, g remains same, density is remains same, 9 eta everything remains same, which means v should be same as before. Then v should be same as before. V should be same as before. Then it is reaching the same terminal velocity again. Again, I have two choices, right? One is 2, the other one is 5. In both cases, same terminal velocity has reached. In both cases, same terminal velocity has reached. Difference is, in this one, this part is linear. In this one, this part is linear, right? It is not a linear variation because it was an object reaching a terminal velocity, right? Any object which is reaching a terminal velocity has changing accelerations. So it cannot be linear. It has changing accelerations. It cannot be linear. So the final answer is answer 2. Final answer is answer 2. It cannot be linear. Right? Any object reaching a terminal velocity is having changing accelerations. Right? Next. A blood vessel of length 0.1 meters has a radius of 1 times 10 to the minus 3. Viscosity 3 times 10 to the minus 3. 3 times 10 to the minus 3. Fast flows through the vessel at a rate of 1 times 10 to the minus 7 cubic meters per second. The pressure difference between the two ends of the vessel is take 5 equals 3. Pressure difference, right? This is small tube is, right? A blood vessel. A small blood vessel can be assumed as a small capillary tube. Then we can apply Poisson's equation. Apply Poisson's equation and simplify. V over T equals 5 delta B R to the power 4 over 8 theta L. V is given rate 1 times 10 to the power minus 7, right? 1 times 10 to the power minus 7. Pi is 3, it's given. We need delta P. I need delta P. Radius 1 times 10 to the power minus 3. Then this is 1 times 10 to the power minus 3 whole thing to the power 4 over 8 eta 3 times 10 to the power minus 3 L 0.1. 0.1 means 10 to the power minus 1. 0.1 10 to the power minus 1. Simplify. That's the simplification now. Simplify. 10 to the power minus 7 here, and this 3 cancels, no? See, 3 cancels, 3 to 3 cancels. Then delta P, 1 to the power 4 is 1, same. Then 10 to the power minus 3 to the power 4, 10 to the power minus 12. Over 8 remains here, and here 10 to the power minus 4 remains. 10 to the power minus 4 remains. Right, now if you simplify, 10 to the power minus 4 to 10 to the power minus 12 cancels, and minus 8 remains. And minus 7 to minus 8 cancels, and only 10 to the power minus 1 remains. Right, then subject delta P. Delta P equals, take this 10 to the power minus 1 to the other side. That becomes 10, and cross multiply 8. Then delta P equals 80, which means that is 80 pascals. 80 pascals. 80 pascals. That's a simple calculation. Simple calculation of Poisson's equation. Simple calculation of Poisson's equation. Right? Yeah, that's all for the day. Right, take it down. I'll be allocating another day, day 2, for viscosity to discuss the rest of the questions. Right, now today we have discussed 17 past wave MCQs here. Right, 17, and we'll be having another session. For viscosity. Right, and we'll finish it off. Right, then with that, we have come to the end of today's planned S2A parts. I wanted to discuss. Right, any questions from anything we discussed today? Any questions? Is it all clear? All good? If any questions, feel free to ask. Right, we have discussed 17 questions. Right, a good count during like around 1 hour and 10 minutes of time. Right, and we'll be having another day for viscosity. Right, and I'll be allocating some other days for elasticity and thermal parts. Right, other parts remaining in mechanics. Right, there are a few more things to do in S2S. Right, so we'll be allocating accordingly. You can get all updates. Through my all channels, YouTube, WhatsApp, or Telegram channels. Right, okay, then if no questions, we can wind up. Right, you are just 21 weeks and through day side of the exam. Don't waste time. Work hard, and put your fullest effort. This is a life-changing time period going on these days. Okay, all right, then if no questions, we can wind up. See you in the next class or next S2A discussion. Right, okay, good night and goodbye. See you.